All right. Welcome back. And here we are in our sequence on structural analysis. And in this video, we're going to be covering method of virtual work, or the unit force or load method for truss structures. And essentially what we're going to do is, hopefully by the end of this video, you'll be able to determine the displacement of a truss joint with a bunch of external loads on it using the method of virtual work. And just to recap here, this principle of virtual work, the idea is to be able to take a structure that has real loading on it, apply a virtual force or moment, virtual external virtual load, in order to get the real displacement. And the idea is that this external work on the left side is equal to the internal virtual forces or loading, times these real internal deformations, internal deformations. And when I say internal deformations, I'm talking about deformation due to internal load. So internal deformations here. And what it is that this really is, the sum of this, internal virtual normal force times the actual real internal deformation. In fact, this should be an integral n over EA times dl. So here, this is that internal, this little n is the internal virtual loading, and then this n over EA dl represents that real internal deformation, or the deformation due to the real loading, internal deformation due to real loading. And really, we have to add a term for each internal loading. So if I have internal moments here, then I'm talking in terms of curvature, plus if I have shear deformations, I'm talking V, the shear, this little v, capital shear for the real shear over GAR times dl. And then if I have an internal torque even in this structure, I would have little torque for the virtual torque, and then the real twist, the angle of twist, dl over gj. This would represent the angle of twist, okay? And so that's really what we're talking about here. And you know what? This summation, this equal to, this whole business is also true for here too. So when I apply a moment, I can induce all these things as well in my structure. But here, what we're going to be dealing with in this video is essentially a single force member for trusses. So with trusses, we have a single force element. So the idea behind a truss is that when you have a truss element, which you do this by making sure all the moments that get introduced to the truss are zero, and when you make a cut in this member, when I make a cut here, internally there is only a normal force N, and that's why it's called a single force member, because there's only one internal load, one internal normal force only, okay? And that's why they call it the single force member. But here, when that's the case, that means when I go back up over here, this moment stuff is zero, the shear is zero, this torsion is zero, and all I'm left with is this right here, this normal force relationship for the principle of virtual work. And what's more is that my joints, because in a truss, they're only connected by joints. I can't apply a moment to it and expect there to be any internal virtual loading, because everything here is just connected by a joint. So this here, I don't need this drawing right here. What this means, what all this reduces to, is when we go and analyze trusses, all we have left is, you're going to have to bear with me here, is this mess right here, which is, if I write this out, which just means that I have to apply some virtual force times that displacement that I want to find is equal to this N times NL over EA times DL. And get rid of that L there right here, right? This N over EA. And if all the areas are constant and the normal force inside each member is also constant, which is usually the case, okay, then I can just do a summation N times N over EA times, let's do this right, N, the internal virtual force, times the real internal displacement NL over EA for all its members. So I equals 1 to N. Let's do P, because we don't use the symbol P for anything. Hopefully, right? But here, this P is defined as the number of elements in the truss. Here. Okay? So really that's why we have just that relationship here. So let's do an example problem where we apply this essentially this sloppily written PV times delta is equal to the sum N times NL over EA. Okay, so this is really it for what this is what our principal virtual work reduces to for truss elements or structures with just truss elements. And so let's go down here to this example problem. And in this example problem, we will start this example problem in the next video. See ya.